The pipelining idea is based on sharing the hardware resources among the instructions. And this could be the same as overlapping the execution. And here is a pipeline analogy where you have a pipeline laundry. So let's say you have a washer, a dryer, and then you need to fold, and after that you put clothes in a drawer, and each of these parts needs half an hour to finish. And let's say that you have 4 loads: load A, load B, load C, load D. Let's say that load A for student A, load B for student B, and so on. So if you don't share the resources, load A will hold every step. It will hold the washer, the dryer, the folding bench, and the drawer. It will hold all the resources for itself, and nobody can use any of them until A completely finish. And then B will start and finish, hold everything for itself, and C and also D. And as you can see, if A takes 2 hours, those 4 loads will take 8 hours. Now, the logical thinking is you share the resources or you pipeline the process. And this happens when A is using the washer, nobody can start yet. When A moves to the dryer, B can start washing. And when A moves to the folding the clothes, then B would be drying and C can start. And at D, which is an interesting point, when D load starts, A is putting the clothes in the drawer, B is folding, C is drying, and D is washing. And here, all the resources are used among the different loads. So if you assume only 4 loads, the speed up would be from start to the beginning. Each one of them will take 2 hours. So all of them will take 8 hours. And for this, from start to end, it will take 3.5 hours. So the speed up would be 2.3 only. Now, the ideal case, if you have a non-stopping loads, and this instructions would be thousands and thousands of instructions, which is usually the case. So what happens, you want this, where this cycle or at this time, all the resources are busy. So you are utilizing all the hardware. And you are sharing this among different instructions or different loads. So you want this to be repeating forever, if you can. So assuming you have n loads, and n is big number, the speed up for this case, you would have each load will have 2 hours, so 2n. And for this case, you will see that each load, if you have many cases that having this, where there is a blue washer and you repeat this for n time. So each one, it's like each load is taking only half n. To take only half an hour to finish, or half n, where n is the number of loads, plus 1.5, and this 1.5 is actually 1, 2, and 3. Each one of them is half. So it's 1.5, which is the beginning. And then you start what I call the norm, where all the resources are shared. So as you can see, if n is too big, this value will diminish. It's almost nothing. And the result will be approximately 4. And it's interesting that 4 is actually the same as the number of stages. So that's the speed. Now, in moving to MIPS pipelining, we have, instead of the 4 stage in the laundry example, now we have 5 stages. Those stages are the instruction fetch from the memory, the instruction decode and register read. So be aware that we call it decode, but there is also a register read as well. And then we have the execute, where you execute the operation using the ALU, or calculate the address in case of load and store. And then you use the memory, you access the memory, some instructions access the memory as we explained. And the 5th and last stage is the write back, or write the result back to the register file. So we denote them by these letters, or we just simply call them F for fetch, D for decode and register read, X for execute, M for memory, and W for write back. Sometimes we use this donation or this letters to indicate each of the stages, and sometimes we use these abbreviations. Now, if we calculate the pipeline performance now for the MIPS, and if we assume that for stages that read or write the register, meaning the decode stage, where you decode and register read, and the write back stage, they take 100 picosecond, and all the other stages 200 picosecond. And we're asked to compare the pipeline data path with single cycle, that the path for these instruction, load, store, R format, and branch. You ask yourself, for each instruction, what are the stages that we are going to use? For all the instructions, you will definitely fetch the instruction and then decode and register read. So these 2 stages are all the time used. For our MIPS, we also have to use the ALU for these instructions, the load, store, the R format, and the branch even. Now, after that, for the memory access and the register write, they differ. Some instructions use them, some instructions they don't. So let's see, for the load, you fetch, decode, and register read, you execute, and then you access the memory because this is a load. And then you load or read the data back to the register file. For the store, you do the 3, and then you access the memory, but there is no write back. For the R formats, you fetch, decode, and register read, and execute, but you don't access the memory. You write back right away. And for the branch, you fetch, decode, and register read, execute. There is no memory access. Since this is a branch, you compare the registers and then go to the target. And there is no write back. And this is the same thing that I remind you of. The store and the branch, there is no write back on them. So, and now we can calculate everything that is register read or register write is 100 picosecond. Anything else is 200 picosecond, and you sum the time. The load will take 800 picosecond, and the store 700, R 600, and the branch equal 500 picosecond. And you can see that the critical time, or the instruction that takes most of the time, is the load instruction with 800 picosecond for the 5 stages, for the 5 different stages. So let's see the pipeline performance in both cases. The first case is called the single cycle, which is using the simplified version of the processor. And the second is the pipeline. Sometimes we call the single cycle the non-pipelined version. So the single cycle or the non-pipelined, the cycle time for each instruction, if you have 3 loads, is 800, followed by 800, followed by 800, and so on. Even if the instructions are load and store and R type, each one of them should take the same cycle time, which is 800. So for example, if this one here is a store, and we know that the store takes 700 picosecond, it will spend 700 of the 800 picosecond executing the store word, and then it waits for 100 picosecond, because you want to unify the cycle time for all the instructions. So at this point, we say that the cycle time is the worst case, which is the load. For the load instruction, took 800 picoseconds. So it's quite easy to find it, the cycle time for the non-pipeline version. Look for the critical instruction that has the critical path, which is usually the load, and calculate how much you spend for each stage: fetch, decode, execute, memory, and write back. Add them together, and we found that they are 800. That's it. For the pipeline, now you share the stages between the instructions. So the hardware for the first stage, which is the fetch, the second will do the instruction fetch while the first is doing the decode, and the last one here, it will fetch while the other one here is decoding, and the first will be executing. I used E, I can use X as well. Sometimes we use X or E for the execution. Now, if you want to calculate the cycle time for the pipeline, it's actually quite easy. You just take the maximum of the stages, the maximum time of the stages. So as you can see, from the get-go, we said 100 picosecond for certain stage, 200 for other stages. So we know that the pipeline cycle time is 200 since it's the maximum. And you can see it when we draw this timing diagram, the single cycle timing diagram, or actually this is the multi-cycle timing diagram. We found that this is taking 200, and when it's 100, we had a gap here where we do nothing, and then do the register read. It's also good to notice that when you are reading from the register, you are reading in the last half of the cycle. When you are writing to the register, you are writing in the first half of the cycle. This way, when you have two instructions, both of them accessing the register file, this could happen because one of them is working on this half and the other will work in the first half. So now we can find the cycle time quite easily for the pipeline, find the maximum time of all the stages. And for the non-pipeline or single cycle, you get the critical instruction, which is the load, and count the stages for the load. And we found that they are 800. And if all the stages are balanced, in the example that we just mentioned, they are not balanced because some stages having 100 picosecond, while other stages having 200 picosecond time. So if all the stages are balanced, which means that they take the same time, then the time between the instructions in the pipeline, or basically the cycle times of the pipeline, is equal to the cycle time if the non-pipeline divided by the number of stages. So just to make the same thing for this example, if we say that this is 200, so all of them are balanced, then the load will take, instead of the 800 picosecond, it will take 1,000 picosecond or 1 nanosecond. So here we'll have 1,000 picosecond, 1,000 picosecond, and the pipeline won't be affected. We just fill up this one and fill up this one. So they will have the pipeline cycle time will be the 200 picosecond. So you can find this 200 picosecond if you say, okay, I have the cycle time for the non-pipeline, which is 1000, and I just divide it by the number of stages, which is 5, and you get 200 picosecond if you want to apply this formula. If they are not balanced, the speed up is going to be less. The speed up due to increased throughput, and that's the idea of pipelining. The latency, which is the time for each instruction, it doesn't decrease. It's actually the same. If you look at for example, the load, how much time does the load spend to finish? So it will spend 200 and 200 and 200 and 200, another 200. So they will spend 1000 for the load only. So they don't, for each instruction, you don't see it, the advantage. If you look at the overall throughput, then you gain big advantage in terms of speed up. Just to remind you how to calculate the speed up. The speed up between two designs or two methods like the pipeline and non-pipeline, you take the time that takes or the larger time. In our case is the non-pipeline time. So you take the cycle time for the non-pipeline and you divide it by the cycle time of the pipeline to get the speed up. So in our case, it was 800 divided by 200, which is equal to 4. So the speed up is 4 in this example. If we assume that they are balanced and this one would be 1000 instead of the 800, then the speed up is higher, where it would be 1000 divided by 200, which is equal to 5. And this is what we mean. If they are not balanced, this is not balanced, and this one is balanced. So if it's not balanced, the speed up is actually less. So pipelining and ISA design, MIPS ISA design for pipelining. And this is great. And the reason is we make things easier in a short sentence. By having all the instructions with the same, they are all 32 bits. This is easier to fetch and decode in one cycle. Contrary to the x86, it has 1 to 17 bytes instruction. It makes it different. We have few and regular instruction formats. We have only 3, the I, the R, the I, and the J type. You can decode and register also in one step without a problem. Load and store addressing. We can calculate the address in the 3rd stage, the execute stage. And then we access the memory after we prepare the address in the stage right after that, which is the 4th stage. The alignment of memory operands makes the memory access takes only 1 cycle because you don't have to worry about readjusting and making things aligned. They are already aligned by definition. Now, the pipelining looks it looks good. It looks that it's the right path to go. However, there are obstacles along the way, and one of them are the hazards, or actually the major one are the hazards. The hazards are situations that prevent starting the next instruction in the next cycle right away. So what happens? You have to wait because of these hazards. So instead of, for example, this case here, instead of going right away and executing this fetch right after this finish the fetch, you can't execute the fetch. You have to push the pipeline a little bit because of these hazards. Now we need to understand what are these hazards, what causes them, and how to deal with them. So there are 3 types of hazards: structural hazards or structure hazards, data hazards, and control hazards. The structure hazards, it happens if a required resource is busy. So if it's busy, you cannot use it. You have to wait until it becomes free. The data hazards, you need to wait for the previous instruction to complete. So you get the data, and based on the data, you can do the next instruction or perform the next instruction. Usually you wait because you are waiting for the value to be updated. So you see the relation between the read and write in the data hazard. The control hazard, it happens when you are deciding on control action, which depends on the previous instruction. And this happens on the branch. You're not sure in the branch. Is the branch going to be taken and you jump somewhere else, or not taken and you go to the next instruction? So these causes delays in the pipeline because you need to wait. Now, the structural hazards in a little bit of detail. It's a conflict for using a resource in MIPS pipeline with a single memory. If you have a single memory, then loading and storing requires data access. What if you have 4 load instructions? Load, 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 followed by another load here. So the instruction fit would have to stall or wait or bubble or do a no operation. All these 4 terms are the same. So stall, bubble, wait, or no operation. They all indicate the same thing. And the reason you can see it here, because we assume a single memory for both the instruction and the data, this 4th load cannot start right away because you need to fetch the instruction accessing the memory, and at the same time the first instruction is accessing the memory too. So this guy, or the 4th load, wants to access the memory. Oh, I can't. It's held by the first load. And to rectify this, we simply separate the memories. We make an instruction memory and a data memory. So the pipeline data path require separate instruction in the data memory or separate instruction or data caches. And this way, if you have them separate, then they can run at the same time, because this load, the 4th load, accessing the instruction memory. So the data memory is free for usage. Or actually, it's the other way around. The first load is holding the data memory, and that's fine for the 4th load because it doesn't need the data memory. It's actually needs the instruction memory for fetching. So the structural hazard, if you don't or you don't want to have it, or you want to rectify this situation, add more resources or split the resources, as you can see in the data and in the memory. Now, for the next type of hazard, the data hazard. Well, we have dependencies or the dependency types that could lead to this kind of hazard. Those dependency are 3 types of dependency. We have the row dependency, which means read after write, and it calls also a data dependency. We have war, which is write after read, and this is the anti-dependency. And we have woe, which is write after write, and this is called an output dependency. So we will check all 3 of them, and we will see that this one, the row, is actually the one that causes the hazard for us. So the row data hazard happens if an instruction depends on the completion of the data access by the previous instruction. And here's an example. It's read after write. So the write happens first, and then after that, the write happens. The write happens first, and then after that, the read happens. And this is what happens in this instruction. Here, we write to S0 as destination, and the following instruction needs or reads the same register. So this is write, and this is read. And the hazard is you read after the write. It's a row hazard. And what happens is, as you can see in the pipeline here, when this instruction, the first instruction, you had it works normally. You fetch and then decode and execute and memory and write back. You're expecting the next instruction to have its fetch here, but it cannot start fetching here because it's waiting for this to be ready. And at this point of time, it won't be ready until you write it back here. It will be ready only when you write back right there. So this means that the next instruction can have this supplied to the ALU for execution only at this time. So you can prepare the fetch and decode before the execution this way. Notice that in the timing diagram, you can't go back. It's like you cannot go to the past. You cannot go back to the past. You can only the lines that goes this way are allowed. Any line that goes backward this way are not allowed. So the result after you write it back to the register, which is S0, can be read as early as possible this way when you supply it to the ALU, so you can do the fetch and decode before this, which means that this one or this instruction cannot start here. You cannot fetch it here. You can't even fetch it here. You must fetch it right there. So you have bubbles here and there. So basically you are waiting for 2 cycles. You cannot fetch here nor here. You're waiting for 2 cycles for the next instruction to work. So if you weren't aware of this, you would start it right away. But because of this direct dependency, we had to wait for 2 cycles. We will add more things along the next slides when we talked about forwarding, where you can actually start them earlier. But at this point, to understand the row hazard, this is the penalty of the row hazard. You had to wait for 2 cycles, and we will try to find a way to make it better. Now, if I ask you what ways you think that could help us, you'll probably spend some time to get this. And the idea to make this to avoid waiting for 2 cycles is called forwarding. This is the famous name for it. It's also called bypassing. And this reduces the number of stalls. This is another name. We have the stalls, wait, bubbles, no operations. So you reduce the number of stalls used for forwarding, used by doing the forwarding or the bypassing. So the idea is use the result as early as possible. Whenever it's ready, use it. Do not wait until you get it written back to the register file. The moment it's ready, you can get it right away. And to have this advantage, you need to add more hardware to the CPU or more hardware to the processor. You need to add more hardware for implementing the forwarding, and we will check this inshallah. So here we have execute, we fetch, decode, and then we execute. When the execute happens, since this is an R type, we can get the result as early as here at this point, and we can forward it to the execute unit of the next instruction, because it needs it, because there is a data dependency between the on the S0 here, which is the row hazard. So we fix it by forwarding. We got the result as early as we could from the execute. We didn't wait until it is written back. And since we are forwarding to the execute, we can decode and fetch. And you can notice here that the fetch started right away, and we didn't waste any cycle. There is no bubbles at all. So comparing this to the previous slide, here, since we don't want, if you don't add anything to the hardware, then when you get the result in the write back, you will only have the result ready when you're done with the write back, and you supply it to the execution, or supply to the ALU in the execution stage. And going back, fetch and decode, here you have to wait 2 cycles. But since now we are getting the data as early as possible with the payment of more cost in terms of hardware, then you can forward from this result to this input of the ALU in the next instruction. And this way you don't wait any extra cycles. So this helps us a lot. The forwarding make the performance better by managing the raw data hazard. Now notice here that we have add, which is R type, followed by R type. Now, in case you have load followed by an R type, you can see that the row dependency on S0 is there. So we have the row dependency, and it caused us, or it made us pay a cycle or a bubble, even with forwarding. So if you assume forwarding, for the load, it won't be ready until you load it from the memory. So the result would be here. S0 would be here. You will load the data in the S0 as early as possible. You can access it right here after the memory. Because the load, you need to fetch, decode, execute, and after this, you access the memory. And now you can forward it to the execute stage of the second instruction. And going backward, you can fetch and decode. And this way, you still need to wait for 1 cycle or 1 bubble. So basically, what we're trying to say here, if you have a load instruction, you can't always avoid the stalls by forwarding. Sometimes you had to pay. And this example, you can see that you pay for 1 cycle. There are other ways to try to avoid this by code schedule. If you reschedule your code, you can actually avoid some of the stalls or all of them together. So if you have this code and you need to reorder the code to avoid use of the load result in the next instruction. If you want to avoid the use of the this stall, so you don't want this to happen. What happens is basically get the sub or the subtraction instruction away from the load for a little bit. Don't make the subtraction right after the load. If you try to, or if you figure out a way to separate them by at least 1 instruction, you can get rid of this bubble. Or basically what you are trying to do here is inject an independent instruction right here. And this is what happens in this code. So assuming that this code is doing A equal to B plus E and C is equal to B plus F. So this code, you need to load those operands, and the B is shared. So actually you are loading 3 variables, 1, 2, and 3 variables. You load only these variables. If we say that all variables are in memory and are addressable as offsets from T0, so you have T0 here, and this is offset 0, offset 4, offset 12, offset 8, offset 16. So based on the offset, you can get those variables. If we assume this, and we have this current code, we have load, followed by another load. So we load the first one, the first variable, and then we load the second variable. And then we did the add between those two variables and get the result in T3. And then we store the results in some place. And then we load the other variable, which is the other one here. And then we add it to the running sum. And then we store the result. So what happens here, if you were asked about only the load hazards that happens here, you can see that you have a load and followed by an instruction that needs the same register. T2 are used here and here. So this is a row hazard. And because it's load after an R type, you need to stop. You must stop for one cycle. Similarly for this one, you have load followed by add, and you have the same register T4. So you also need to stop. You need to wait for one cycle. And because of this, you need, this code needs to finish in 13 cycles. Because the first instruction the first instruction will take 5 cycles. For each of the 5 stages, it will take 1 cycle. So it needs 5 cycles. And then each following instruction will have 1 more cycle. So this will spend 1 more. This will spend 1 more cycle, 1 more cycle, 1 more cycle, and 1 more cycle. So it's 5 plus 1, 2, 3, 4, 5, 6. And that's 11. Plus those 2 stalls, which is 2 more stalls. So the total is 13 cycles. Remember, in the pipeline, the first instruction only will take 5 cycles. And then every subsequent instruction will take 1 more cycle. Plus the stalls based on the hazards that you have. Now, what happens here is we reordered the code. Basically, we moved this load upward because the mentality here is load everything at the beginning and then do the other instructions or do the work. By doing this, if we move the load upward this way, now we will move the add away from this load because this load will go there between them. So we push the add a little bit down. And this dependency now, we have an instruction injected in between. Only by doing this move. Not only this, we also make the load away from the add. So by doing only one instruction movement from this position to this position, we get away, we make a space between the load and the add, and also between this load and this add. Actually, we have 2 instructions. And because of this, we don't need to stall anymore. So we don't waste those 2 stalls, and we have only 11 cycles. So basically, we can do code scheduling to avoid the stalls. Now, for the other types of data hazards, we have the war hazard and the woe hazard. The war hazard, the second instruction write the destination before it is read by the first instruction, which means you read first. Here we read S0, and then in the second instruction, you write the S0. For the wow, the second instruction writes an operand before it is written by the first instruction. So this is actually write after write, and you can see in this example, you write to S0, and then in the next instruction, again, you write to the same S0. So this is write after write. Remember, we have row, and we have those two, the were and the wow. Those three dependencies might cause a hazard based on the MIPS. For our, based on the ISA. For our MIPS ISA, row is the one that caused trouble for us, and we need to fix it. And we already show you the ways to fix it. The war and the wow, to answer this question, they don't cause troubles for the MIPS pipeline, or maybe another pipeline with many stages or with different hardware. They might cause troubles. So it's good to be aware of their definition at least. Also, you might think, why don't we have row after or read after read? This will definitely not cause anything for me, no problems. The problems happen if an update happens. If an update happens, and the update happens only when you have a write somewhere. So this doesn't cause any problems in any architecture. Now, this is a dependencies example. If you were asked to find all the row, war, and wow dependency in this code, I named each instruction by I0, I1, and so on. And I want you to find the row, the war, and wow hazards for all of them. To do it correctly, you start by the first instruction and you check the row hazard, which means here you are writing to T1. So check for all the subsequent instructions. Where do you read T1? Do you read T1 here? No. Do you read it here? Yes. So this means there is a dependency from I0 to I2 on T1. And this is what I write here. We continue. Check the other one. Is there T1 here? No. Is there a T1 here? No. Is there a T1 here? Yes. Is it a read? Yes, it's a read on the add instruction. So from 0 to 5, we have it on T1. Is there a T1 here? No. T1 here? Yes, there is a T1, but it's a destination. So this is not a row hazard. It's another hazard. We'll come to it. Now, you do the same for the instruction I1 and be aware of the instruction type. This is a load. And because this is a load, this is a destination. Since this is a destination, this is a write for sure. So we have a write. Is there a read after write? Is there T2 read anywhere in the subsequent instruction? Yes, it's read here. So there is between I1 and I2 on T2. And you keep looking and you won't find anything else. Now going to the next instruction, I2 or T3. Now it's written here. Is it read anywhere else? You will keep looking. You might think that there is nothing because this is written in the store. Be careful. The store doesn't write anything. This is actually read, and this is also read. So you read T0 when it's a store. You also read T3 because this is a store. You read the data and you read the base register and you add the offset to it. So this is basically a write, and then there is a read after that. So this is read after write. So between I2 and I3, we have it on T3. So be aware. Don't think that if the register in the beginning, then it must be written to, or it must be a write. I look for the read after that. No. Be aware of the store. That's one case that both of the registers are only source register, or you read from them. Another instruction is the branch equal. The branch equal, you read the registers on. There is nothing to write actually. After this, you keep looking for T3 in the instruction 2. You keep looking here, and there is no T3 anywhere. Now we move to I3. Now the I3, there is no written there is no registers that you write to, so you don't have to worry about it. The store, you don't have to worry about it. There is a case, but we will look at it here. Now for the load, for the instruction number 4, we have a write in T4. You look for a read, and you found a read here. So from between 4 and 5 on T4. And you'll also find between 5 and 6 on T5. And this is an add followed by the store, similar to this one on T3. So that's the row hazard. For a war hazard, you have a read first, and then you write. You can see here we are reading T0, and it's not written anywhere. Again, T0 is not written anywhere. Here we have a read on T1 and T2, but they are not written anywhere here except on the last one, which is 7. So this is read, and here it's written to. So there is a dependency, a war dependency between I2 and I7 on T1. Now, you check both operands. We checked T1 and we found that we write it here. You also check T2 and you won't find it written anywhere. So you check for both operands. Now, for this store, it's a war dependency. So there is a read, and after this, there is a write. This is a read. This is also a read. And you found that you don't read T0 anywhere. I'm sorry, you don't write T0 anywhere. You also don't write T3 anywhere, so there is no dependency. Similarly, for this instruction, you will reach to a point for this I5 here, and you check the two operands, because this is read, T1 is read, you read T1 and read T4 on instruction number 5, and you look for the other instruction where you write them, and you found that you write it in the last instruction I7, so there is a dependency between I5 and I7, which is on T1, and this is a war dependency, as you can see. The last dependency, which is a wall dependency, write after write. This is one of the easiest. In my opinion, this is easier than the row or the war, because you look for write followed by a write and the other instructions. So you write T1 here, and you found that you also write it here and 7. So there is a dependency between 0 and 7 now. T1. If you check the other instruction, you won't find any other instruction that writes on the same register. So this way you got all the dependencies. Now, if you were asked what kind of dependency between the two instructions here. So from the get-go, you will think that, okay, we have T1 here. You write to it, and you also read it here. So be aware that this here you read. So this is read after write. Read after write dependency on T1 between instruction 8 and instruction 9. There is also another dependency between this and this. So here in the load, you are reading. And in the store, you are writing to this memory location. So there is a word dependency from I8 to I9 on memory location T0. But in our hardware, we only cares about registers, not memory locations. So differentiate between registers and memory locations. You need to resolve this problem, but that's not related to the hardware of the processor, it would be related to the memory itself. But this dependency is there. So there is a word dependency between I8 and I9, and you can say this is right after read on this location. If you look for this similar situation, this code, you cannot find it because the locations are different. We have 0, 4, 12, 8, 16, and so on. So they are different than each other. Okay. Now for the control hazard, up to this point, we discussed the structural hazard and also the row, war, and wall dependencies and the hazard that caused because of it. Now we want to discuss the control hazards. This comes from the branch instruction. Whether it's branch, sometimes it's the jump, cause similar behavior. So the branch determines the flow of control. You are fetching the next instruction depends on the branch outcome. The pipeline can't always fetch the correct instruction because you're still working on the ID stage on the branch. In MIPS pipeline, branches cause control hazards. And the branch causes that because the branch needs to compare the registers and compute the target address. Because it's busy doing these jobs, you cannot know at the same time it's trying to execute those jobs, you can't know what is exactly the next instruction. So you need to wait a little bit until this finishes and gives you the result. So it's wise to add the hardware as early as possible in the deadline. And we want to do it in the ID stage. This way we don't have, if we do it in the ID stage, this way we won't waste a lot of cycles. So because we are moving these two jobs to the ID stage, we need to update the hardware as well. So we will assume the branch resolved in the ID stage in all the slides from now on, unless it's stated otherwise. Now, to understand this better, here is a stall in the branch. Let's say that you have this instruction. You add register 5 and 6, and then you put the result in 4. Okay. And then there is a branch instruction after this. So the branch compare those two registers, and based on them, you might branch to this label. So you are not sure. Should you execute the next instruction, which is the or jump to the other branch? So at this point here, we will assume that this is the correct instruction, but you are not sure unless you do the decode stage for the branch. So at the end of the decode stage, for sure, you know what is the next instruction. So this, whatever it is it the next instruction, or is it the first instruction of the target address? You can start it only at the end of the decode stage of the branch instruction, because at this point, you know exactly what is the outcome of the branch. Do you branch or not? This means that do you branch or not at the end of this decode stage. So at this point, you do the fetch, and because of this, you cannot do anything here. You need to wait for one cycle. And that's basically the whole idea. To explain it in another way, here's an instruction. You do a fetch, decode, execute, memory, and write back. You only know the outcome of the branch instruction at the end of the decode stage. So to minimize this problem, or to take out this bubble, if we can, what we do is a branch prediction, where we predict the outcome of the branch here, and then compare this prediction to the actual at the end of the ID stage or the decode stage. So longer pipelines can't steadily determine the branch outcome really early. And because of this, you need to stall for some cycles. Luckily, we're only having one cycle because we pushed all the calculation to the ID stage, which is a good point. But even with that, we still need to wait for one cycle. Another way to make it or to reduce this penalty is by predicting the outcome of the branch here. So if you predict and your prediction is correct, then you don't waste any time. But if you predict and your prediction was wrong, at that time, you wasted the cycle. So that's the case here. You only stall if your prediction is wrong. In the MIPS pipeline, you can predict branches not taken. So if we say that all the branches in MIPS pipeline, in this case, if we assume that they are not taken, so you execute to the next instruction all the time. So our prediction is this. We will predict here that the next instruction is BC +1. Sometimes we will get it correct, sometimes we will get it wrong. So what happens now? You will see it in the next instruction. Now, if your prediction is correct, you notice that we don't waste, and there is no bubble, we wasted no cycles. But if the prediction is incorrect, then you have to insert these bubbles, or you are wasting one cycle. To see this, let's see this instruction here. Let's say that here in the branch, now you are deciding if the branch is happening or not in this stage. Here, you make a prediction, and your prediction is get the load, which is the next instruction. And let's run it in the pipeline. And here, when the load is fetched, at this point, you can see if it is really true and the load is the one that is after the branch or not. If it is correct, then you just continue and no harm is done. And that's good. But if your prediction is wrong, so your branch is here, you made the prediction here, and the actual result, you got it here, then even if you get the load, let's say that the load was here, and it was fetched right there, and at this point, you know that it's not the load, it should be something else. Then you need to take the load out. You insert those bubbles, so you will waste one cycle, and then you get the correct instruction after this, which is, it happens to be this open. So the prediction is actually helpful. It's reducing the cost of the stall. And our prediction that we assumed, the prediction is that the branches are not taken. And we will talk more about prediction and what are the other choices that we have later on the slide. Now, a more realistic branch prediction. We have actually two types, the static branch prediction and the dynamic branch prediction. The static, it could be like our example that we said, we predict that all the branches are not taken, or maybe you say that if you are branching backward, predict that the branch is taken. If it is forward, then it is not taken. But both of these examples are static branch prediction. There is a better choice, which is the dynamic branch prediction, where the hardware measures the actual branch behavior. And this happens only if you record history, which means what happens in the last time we called the branch, did we predict taken and it was actually taken? So our prediction was correct. And based on this, you predict the next branch. So you record history. So let's assume that in our past history, if we predict not taken, then our prediction would be correct. So it's wise next time to predict the same. So that's the dynamic branch prediction. You need some places to store history, and you need to know which history you need to store. Do you store the history for all the branches altogether, or for each branch by itself, you record its own history, and so on. You assume future behavior will continue the trend, and this is the main idea behind the dynamic branch prediction. Now, when your prediction, even with the dynamic branch prediction, could be wrong. When it's wrong, then you have to add this bubble or stall. You wait for some time and refetch the correct instruction and update the history that you are keeping track of accordingly. Now, I need to say that more of this will come in the next slide. Now, as a summary, the pipeline improves the performance by increasing the instruction throughput. It actually executes multiple instructions in parallel. Each instruction had the same latency, as we said. It's improving the performance, even though it's improving the performance by like a really good amount. If you compare the non-pipeline to the pipeline processor, but it is subject to hazards. So you need to worry about when to introduce stalls. When do you introduce those bubbles? And we talked about the structure, the data, and the control hazards. And the instruction set design affect the complexity of pipeline implementation. So you gain a lot of advantage in terms of performance with the pipeline, but it comes with its problems. Now we will talk about the data path of the pipeline. We will start from our data path that we have in the simplified version. So what happens is we will break it down into stages. And we know that we have 5 stages. The instruction fetch, and this is the instruction fetch here. This is the instruction decode. So this is the execution stage, and this is the memory access stage, and this is the write back stage. These are the 5 stages. So basically what happens, we took the simplified version and we sliced it into stages. Of course, you need to make decisions. Like, for example, this part, the part that has the BC+4, we took the BC+4 and we put it in the instruction fetch. Now, what about calculating the target address of the branch? Right now, it's in the execute stage, but we want to push it to the ID stage, and we said that. And this is what will happen when we follow slides until we reach to the final design. But right now, here's some of the things that you should be aware of. This is right to left flow, which leads to hazards here and here. So anything that has a backward behavior or a feedback, this could cause hazard. So this blue line could cause a hazard. Also, this blue line could cause a hazard. You notice that this line is actually the write back behavior. Do you write back from the ALU or do you write back from the data memory? Those could cause hazards. And we know that this is the row hazard. When you write back, and if the instruction that or the read register is the same as the write register of 2 instructions, and you have first the write and after that you have the read, this could cause a hazard for you. Similarly here, but here is the branch, the control hazard. So when the branch happens and you are updating the BC, this could cause a stall for you because of the control hazard. So basically, this is the row hazard that could come back from this blue line, or and this one is the control hazard that could happen when you have this blue line coming back to the BC. Now, at these slices, we will introduce the pipeline register. So we need registers between the stages to hold the information produced in the previous cycle. The reason is we want an instruction running in this stage and a different instruction running on this stage, a different instruction running on this stage, and here and also here. So there might be a load instruction here, and at the same time it's accessing the memory, there is an add instruction that is decoded here, and there is a sub instruction that is just fetched from the memory, and there are different instructions here. So let's say that there is OR instruction and AND. So this AND needs its status with us. The sub just started, so it will have all of its information related to it with the instructions. But the add, it's here. So when it was fetched in the previous cycle, we should have saved every value that need to be saved in the in this IF/ID registers. Similarly, for the OR, it needs its registers and anything related to it right there. The load, it needs the values here, and the add needs its values here. So these registers are called, this is the pipeline register between the fetch and decode, because we know this is fetch, decode, execute, memory, and write back. This one between the decode and the execute, and this one register, or this pipeline register between the execute and the memory, and this one between the memory and the write back. Now, what kind of information are you saving? For example, in this one, you should save the BC plus 4. The result of BC plus 4 should be stored here. And along the way, you should keep it here until you might use it here when the instruction moves to different stages. Similarly, you should save the instruction here. Here, you should save read data 1 and read data 2 and the sign extension. Similarly, here you need to get the outcome of the target address here and the outcome of the ALU, and also the data of the second operand of the register file in case you are having a store. Similarly, here you save the outcome of the data memory in case you have a load, and the outcome of the ALU in case you have an R-type instruction. Among other things as well, this is just some of them. You need to save the controls. You need to save anything that is between two stages, and you save them in the pipeline registers. So that's a hardware cost that you need to apply to your hardware to make it pipeline. Now, the pipeline operation happens cycle by cycle. It has cycle by cycle flow of instruction through the pipeline data path. You have a single clock cycle pipeline diagram where you have only a single clock cycle, and you are checking what's going on in this clock cycle. It shows the pipeline usage in a single cycle and highlight the resources that are used in that cycle. Now, the multi-clock cycle diagram, it's actually a graph of operation over time, and we have many examples before. I'll go back in the slides to show you many of the multi-clock cycle that we already have seen. This is a multi-clock cycle. pipeline, because you see what happens in the time. And if you have multiple instruction, what happens here, what happens here, what happens here. So in multiple cycles, what's going on in the pipeline. So that's a multi-cycle pipeline diagram. Similarly here, this is a multi-cycle pipeline diagram. And many examples. This one is multi-cycle, this one is multi-cycle, this one multi-cycle, this is multi-cycle. Even the idea of pipeline, when we introduce it at the beginning, in the laundry example, this is a multi-cycle pipeline diagram. Similarly also here. So, going back, the multi-clock cycle diagram, it's a graph of operation over time. We will look at single clock cycle diagram for load and store right after this slide. And the multi-clock cycle diagram, we've seen many examples. And we also will see a lot of examples in other slides. Now, for the load, it will start fetching here. And when you fetch, you will have BC plus 4. You need to calculate the next instruction. And you will get the instruction from the instruction memory and save it in the pipeline register. You will save the instruction memory and you will save the BC plus 4. Also, this load, this mux should be activated, indicating that the result of the BC was the address of that load. So you are using these resources at this cycle. The next cycle, the load will move to the next stage. And you can see it here. What happens? You will decode. Notice that we have lines coming out for the instruction that were saved in the register, the pipeline register. You decode here, and you use the registers from the register file. You should get the register that comes from here. And you also get the second register, but for a load, you care about what happens in the sign extent. So you get the immediate value, you sign extended, and you know that you need the first address as the base register and the offset to add them together to get the correct address of the data memory. But you won't have it for the data memory at this point. You just save it in the register. Also notice what happens. Here in this register, you are reading in the latter half cycle of the register. And here you are writing in the first. So you read in the latter half cycle and you write in the first. Now, what happens if the load moves? When you move, you need to get the correct control in the mux to get the sign extended value and also to get the operand. But you notice that you don't get it from the register, you get it from the saved pipeline register. You don't get it from the register file because this happens in the previous stage. So you get it directly from there. We don't use this because this is not branch. Now what happens after that? The load will access the memory. Let me go back. Now, after it do that, it will get the result, which is the address of the data memory here, and save it in the register. And it will also save the result of the second operand, just in case it's a store. But at this point, it's a load, so it's not gonna use this one. So when you move to the next stage, now the address is ready. You access the data memory and get the data and save it in the register between the memory and write back. Similarly, this one will be saved here in this register in case it's an R type. But since we have a load, we worry about this. And at the write back, you will get the result back and you write it in the register file. But you might think everything is fine here. If you are in pipeline, worry about all the details. Here's one of them. This is actually the wrong register number of the write back. And the reason is, here you are doing the write back, so you will choose, because it's a load, you will choose this one. And then you will write back here. You get the data. The data, you got it correctly. And you are writing it back. But the problem is, where do you write it back? The register name is actually the name of the current instruction that is running here. When the load and the write back, there is another instruction that we don't know. Maybe it's an add. And the add has a different register number in the destination. So you cannot write back the load in the add destination. And this needs rectifying. You need to make sure that it is the correct register number, not the wrong one. So to do this, we need, when the load was here, let me go back in the slides when the load was here. When the load was here, we should have kept the register number, this register number, we should kept it here somewhere in the register or the pipeline register, and we saved it along the way, moving forward. We kept it here, and then we moved it here, and we also moved it here. And then when we add the write back, it was here, and we could write it, or we can also read that register number, and we supply it back here. And this is the way we should solve this problem, by introducing what I just said. We get the correct register number, and we saved it here, and we keep it with us in the different stages of the pipeline registers, and it goes back with the correct register number for the write register. So the register number will be needed later in the write back stage, so we need to carry it with us. That's one example. There are many examples that we need to make sure that we are getting the correct data along with the instruction as it moves through the pipeline. Now, this is for the store. The fetch and decode, it behaves as the load. Now, the difference in the execution for the store, it will use the mux, but it will use this mux, and it will needs the sign extended value like the load instruction, and then it will calculate the base register and the sign extended value to generate the address for the data memory when it stores the value. But the difference here that we need also this register, that when we read the register from the register file and we saved it here, we need this data to be saved in here. So when we move to the next stage, we have the address ready, and we also have the data ready for storing. Also, you should know that in the write back, the store doesn't do anything. So here, the operations don't care. So now we see different single cycle diagrams, and you can see for each cycle what happens to a certain instruction. Now, this is the multi-cycle pipeline diagram, and you can see that we can work on many instructions. At this diagram, we have 5 different instructions, and you can see that this is at the fetch, instruction memory, decode and register read, execute, and this is the ALU, main memory or the data memory, and write back to the registers again. You could draw it this way, or you can just make it as I said here. You could say fetch, decode, execute, memory, and write back for short. This is for the load. Now for the sub, it would be fetch. You start from here, decode, execute, memory, and write back. And quickly you can fill up the multi-cycle pipeline. Now, the multi-cycle is very helpful, especially when you have hazards. At this case here, you can find that we have register number 1, 2, 3, 4, 5, 6, and 10, 11, 12, 13, 14. And this is register 1, 2. So if you look for hazards, you won't find any row hazards. This 10, you won't find it anywhere, red. The 11, you won't find it anywhere where it is red. Similarly for the 12, 13, and the 14, it's not being read anywhere. So we don't have a row hazard. Since we have a branch, we don't have a branch. We don't have control hazard. So we don't have to worry about any hazard problems. And the multi-cycle pipeline would be like this. But this also helps us of finding how many cycles I'm spending for this code that has these 5 instructions. You can calculate it this way. This is 1, 2, 3, 4, 5, 6, 7, 8, and 9 cycles. You could also calculate it by knowing that the load will definitely spend 5 cycles, these 5 cycles. And any subsequent instruction will have 1 more cycle. So you have 1 more cycle here, 1 more cycle here, 1 more cycle here, and the end we have 1 more cycle. And you can calculate how many cycles you have: 5, 6, 7, 8, and 9. So we have 9 cycles for this code, which is matching what we have here. Now, this is the traditional form. Instead of drawing it, you could do it this way. But even this will spend some time drawing these rectangle shapes. So it's better to just use fetch, decode, execute. You could use E or X. I think I prefer E because X can be for don't care. So you should write E. Fetch, decode, execute, memory, and write back. Similarly here, fetch, decode, execute, memory, and write back, and so on. And you get the same clock cycles. So that's the short way. This one showing their resources and how they are used. Basically, there is only one information. When you are reading from the last or the last half cycle. So when you read from here, you read from here, and you read from here. When you write, it's in the first half cycle. So these are in the second half cycle. This is in the first half cycle. This is the only information. Other than this, it shows you the register files, or the I'm sorry, the pipeline registers. So this is the traditional form, and you could also have it this way, where this looks like the single cycle, but here we are showing the different instructions. But you need to be careful. Notice that this is the first instruction. First instruction is load, followed by the sub, followed by the add, followed by the other load, and end up with the add. This is the sequence of instruction. So by the time when this 5th instruction is fetched, the first instruction is already in the write back. So the load would be here in the write back. And then that would be the first instruction, second, third, fourth, and this is the last instruction. You just need to be aware of this, not to get confused. Now you can say that the load in the write back, the sub is memory stage, and the add in the execution state. The load, the other load, is in the instruction decode stage, and the add, which is the last instruction, is in the fetch stage. Now, up to this point, we didn't show to you any controls. Now we will try to build the control or the pipeline control step by step. So here is the control. This is the register write. This is the memory read and write. And these are the controls of the muxes. This is register destination. This is the ALU. This is the ALU control. And here we have the memory to register. Here we have the branch. So we need the branch and we need to save the outcome of the comparison to the pipeline register and then read it here. So you can see now, currently, in this diagram, we are doing the calculations of the branch in the memory stage. And we said that we want to push it to the ID stage. And we will figure out the way to push it this way later. Now we will start to get these controls from a control unit. So what happens is the instruction, you fetch it and you will get the instruction here saved in this pipeline register. From here, you can feed it to a control unit. And the control unit will give you all these register or all these controls. But at this point, you need to be aware of here at the, in this stage, the decode stage, we need to give the instruction its register write. In the execute stage, we need to worry about these controls. In the memory stage, we need to worry about the branch, the BC source, and the memory write and memory read. And in the write back stage, we need to worry about the memory to register control. So there are controls for the execute stage. There are controls for the memory stage, and also there are controls for the write stage. For this one, for the D stage, it's actually, it won't cause any problem for us because we will have the control unit in the same stage. So we can supply it directly. But for these ones, we need to make sure that it's going to that stage in the right cycle. So to do this, we will make simple modification from this pipeline register. We will give the instruction and we will feed it to the control, and we will categorize it as some controls going to the execute stage, some controls going to the memory stage. So you need to forward it to the next pipeline register and then feed it to the memory stage. And the last one is for the write back stage. So you forward it 2 times until you feed it to the correct one. So notice that the execute, in the execute stage, you feed it directly. So this is the control. You save it in the register and you feed it directly. For the memory, you store it in the register, forward it, and then feed it. For the write back, you store it in the pipeline register, forward it again, and then feed it. So at this point, here's what happens in the pipeline control. The same idea that we just mentioned. We have the control right here. And we would say that those 3, this is the execute, memory, and write back. The execute will supply you with the ALU source in this one, with the ALU op, which is the 2 control, or ALU op 0 and ALU op 1, and also the register destination. For the memory, you save it and then forward it and feed it to the memory memory write and also memory read. And the branch, don't forget you have a 0 as well from here to get the BC source to the BC for the program counter. Now for the write back, you save, forward and forward again, and at the end you give it to this mux memory to register. And also be aware that the register write is actually not in the decode stage. It is moving from the write back to the register file, because you should allow write for the registers when you are writing back. So this is what happens to the control. Now, at this point, we will see how we deal with different data hazards. So we built the pipeline processor. We showed the single cycle and the multi-cycles, and how the data path is moving, and also the control path. The only thing that we need to worry about, what happens when you have hazards. So we said that we do forwarding or bypassing, and we need to do some prediction. The question is, what are the hardwares that we need to add to the pipeline to make those data hazards go away completely or have less cost? And we will check this in the next video.